very welcome back, everybody. Well, not everybody's here yet, but we have to stick to the timing. So we have to get started again after the coffee break. And so as I said before the coffee break, we will continue with more on the RES4LIVE project, on specific practical installations on farms, on thermal comfort, for example. And the first speaker is Stefano Benni. So please come up and you can start with the defossilization of a commercial swine farm.
Thank you. This research has been carried out by the Biosystem Engineering Group and the Geoengineering Group of the University of Bologna. So we are talking about RES4LIVE project, in particular one of the 4 pilot farms of the project, which is located in Emilia-Romagna in the Modena province. And this farm is Golinelli, and it is a partner of the project. And it is a farrow to nursery swine farm. And it rears 500 sows, 2,500 winners. And the defossilization task of RES4LIVE project focuses on the nursery barn, which is illustrated in the pictures. And in this building, we aimed to develop, install and test an integrated renewable energy source system combining a photovoltaic thermal plant, a geothermal storage, and a modular dual source heat pump. Everything is linked with a smart control system for the monitoring of the environmental parameters and the control of energy usages and energy production. And another smart control system has been implemented to monitor the temperatures underground for the underground geothermal storage. So in detail, the building, the nursery barn, has a rectangular plan layout. It is 62 meters long, 17 meters wide. It has a 2-pitched roof and has a reinforced concrete precast structures. And inside there are 10 nursery rooms and a technical room, which are accessible from a hallway, a lateral corridor, which is placed along the western wall of the building. This space, the hallway, is important for the pre-treatment of the air which is used for the ventilation of the nursery rooms, because the ventilation is carried out through extraction chimneys, and the air, the inlet air, comes from the hallway, and before it comes from outside. So in the corridor it is possible to control the air temperature and the air quality before it reaches the animals. So we combined a system with a dual source heat pump, medium temperature of 35 kilowatt, and a solar photovoltaic thermal system with a power of electrical power of 8 kilowatt, a thermal power of 25 kilowatt, which is controlled by a solar station, and the borehole thermal energy storage, which is in charge of accumulating the excessive heat from the solar panels and to store it underground. In particular, the borehole thermal energy storage system is made of 8 boreholes, and it has been designed and dimensioned on the basis of the thermal and energy requirement of the building and of the economic constraint of the project and of the farm. The boreholes, heat exchangers, are 30 meters depth. They are placed along outside the building, along the eastern side in the farmyard, and they are placed in 2 rows of 4 boreholes. So we have a total of 8 boreholes, and inside each one there are 2 double U pipes, one for the injection of heat and the other one for the heat extraction. Moreover, there are 2 piezometers for the monitoring of underground temperature and the level of groundwater. And we measure the temperature underground every meter. It is important to say that most of the work has been carried out directly by the farm, and the farmyard is completely available again for the farming operation, so no soil consumption has been necessary for this installation. The circulation of the vector fluid is controlled by the solar station, which is capable of controlling the temperature of the vector fluid inlet underground to keep it below 35 degrees, which is prescribed by the regional environmental agency. We can also circulate the water from the solar panels to the underground, or only in the upper part of the circuit, or only in the lower part, to know the temperature, the average temperature in every part of the circuit. In the first summer, we measured the heat production, in particular in May and June 2023, and we assessed the energy production of the solar plant. So we estimated the yearly renewable energy production, which corresponds to an emission saving of 8,600 kilograms of carbon dioxide. Then, in spring 2024, we tested more in detail the geothermal storage. We have a period with high insolation, so great level of solar energy, solar radiance, and we injected 600 kilowatt hour of heat underground, with a difference of temperature between inlet and outlet of 5 degrees. And in the following period, the outside temperature dropped, so we needed heating for the building, and we extract heat precisely 800 kilowatt hours, and with the average difference of temperature between outlet and inlet of 3 degrees. And we can reach a minimum temperature in the vector fluid of 2 degrees below zero. So the heat pump was capable to provide in this period 1,100 kilowatt hour, which are mostly extracted from the geothermal storage, which are 800 kilowatt hour, as we said, and overall the energy extracted was 850, because a small part of energy was extracted from the air through the less efficient heat exchange with air, which was necessary only in a short period. And to provide 1,100 kilowatt hour, only 250 kilowatt hour of electrical energy were absorbed. And we have computed the coefficient of performance of the heat pump, which was totally 4.34, which is very close to the COP of the heat pump working only with the geothermal source, which is 4.667, which is a very high value for a coefficient of performance. And only for a short period it was necessary to use the hybrid heat exchange, which means both geothermal and air. You can see in this curve there are only two slope part of the curves, and in these conditions the coefficient of performance is lower, is 3.50 as it is as it was expected. And with this heating system, it was possible to keep the temperature humidity index within the winner's room between 60 to 75, which correspond to a condition of animal welfare, and to control the temperature inside the corridor within the desired value to pre-treat the air for the ventilation. Further technical data about the performance of the system are that the storage capacity of the solar energy that is available over the solar panel is 40%. So this is the ratio of the solar energy that effectively is stored underground based on the tests we performed. And we have a maximum heat extraction capacity of 26.8, almost 27 kilowatt, but the average heat extraction capacity is 13 kilowatt, which is good for our for the dimension of our heating system, and considering also the costs of the plant. So we demonstrated that it is possible to replace fossil fuel to heat a pig barn, in particular a nursery barn, with a proper design and definition of a combination of renewable energy sources, because previously the barn was heated through a fossil-based heating system. And it is important to have availability of data, so we collect them through the smart control system and the smart monitoring system. And in this way, it is possible to effectively manage the indoor temperature of the livestock barn without reliance of fossil fuel. So it is a pilot case that could be implemented with higher efficiency on a broader scale. Further details are available in the papers published, and I thank you for your kind attention, and I'm available for questions.
Questions for Stefano?
Now online as well? No. I have a question for you then. At the end, you mentioned that you have 40% in April of storage, storage capacity from wind panels. April, it's already long days. What do you estimate going to be in the winter? January, February, when the days are shorter? That's going to...
Okay, 40% is 40%, so we expect that 40% remains the ratio between the heat stored and the heat available over the panel from the solar irradiation, because it was measured in this way. So there is probably the percentage will be the same, even if the absolute value will change over time.
So do you think the absolute value will change, but not the percentage?
Not the percentage.
Okay. Thank you.
Is there another question? I have a question, Stefano, on what was the feedback from the farmer himself, and is it a system that is ready to be recommended for other farmers, or what needs to be done before others can apply it?
The system is ready to work in other farms, in particular for heating with this level of temperatures, so in particular for the preheating of the air, which will then further heated with other systems. In this case, we have thermal lamps. But for heating at temperatures of around 50 degrees of the hot water, it is suitable and ready to be implemented in any farm.
Okay. Thank you very much. So our next speaker is Dimitris Stiris, and he will say something about installation in the laying hen house.
Hi everyone, thanks for being here today. I will start my presentation with what is the problem that you are facing. That even though we can consume in the European Union about 22 kilograms of animal-based proteins, and with the egg production sector alone producing approximately 6.7 million tons annually. The direct on-farm energy use accounts for 3.2% of EU's total energy consumption, meaning that this has an environmental impact that we have to consider. To move towards a more sustainable future of the food production sector, there are a number of initiatives in EU level aiming to reduce the carbon footprint, improve animal welfare, provide us with high energy efficient in terms of implemented technologies that can lead to the climate resilience of climate of food sector in times of climate change. To reduce the fossil energy use and create a more energy efficient and environmentally friendly approach to the management of the conditions inside livestock facilities, and more particularly in laying hen house. In the framework of RES4LIVE project, a heat pump was designed and installed as part of an integrated renewable energy sources system to regulate to control the indoor climate conditions of a laying hen house. In the core of the system, together with the heat pump, we have a PV system producing electricity in order to cover at least part of the energy needs of the farm. The objective of this work was first to analyze the performance of the heat pump as an integrated in a livestock environment, and analyze these results for two typical production periods, one summer and one during summer and one during winter. And of course, understand the potential that this technology, the heat pump, has the potential that it has to enhance the sustainability of the livestock sector in general. Now, moving to the case study of this work, we have the laying hen house in the Agricultural University of Athens, consisting of a room of 45 square meters with a capacity of approximately 400 hens that are hosted in 3 tire and enriched colonies. As mentioned before, the installed heat pump is regulating the indoor space conditions, providing heating, cooling, and dehumidification. And the PVs, the photovoltaic panels, cover part of the total energy needs. The main goal of this system is to mitigate the heat stress of the animals that can enable us to have more production periods even when the temperatures are very high. That can lead to increased production with lower environmental impact. The main feature of the study, the heat pump system, is presented below. It's an air-to-air heat pump with a screw-type compressor. It has a nominal cooling capacity of 10 kilowatts. And it is also equipped with a heat recovery system, as well as auxiliary fans and water pumps. Of course, the heat pump is connected to a smart control system that feeds it with data in terms of temperature, indoor and outdoor temperature, as well as relative humidity that makes its control more versatile. Now, the results we have for these 2 periods that we studied. The first period is between late July and mid-late August of 2023, summer, where the cooling mode was on, only cooling mode. In both periods, dehumidification was not operational. So yes, what we can see is that we achieved indoor air temperatures that are acceptable even during heat waves. For example, even when the temperature was around 45 degrees Celsius, the indoor temperature was 28 degrees, which is not ideal, but yeah, acceptable. We managed not to lose any animal during this period. The set point was at 25 degrees Celsius, plus minus 1. Yes, the maximum indoor temperature was 28 degrees. The cooling capacity of the heat pump was not enough only during extreme weather conditions, and because the ventilation rates were higher than initially considered in the design phase. In terms of energy consumption, the total consumption of the building was approximately 4,000 kilowatt hours, with the PVs covering 22.5% of it, and the compressor contributing to 65% of the total consumption. This is mainly due to the fact that during this period, very high cooling loads were needed, so the compressor was operating almost constantly. We managed to achieve a seasonal COP, coefficient of performance, during these 30 days of 2.42, and for the cooling mode, and for the year of 3.12. Now, in winter, the indoor temperature was mostly within the limits set. The set point was 20 degrees. The period I forgot to mention was the first 30 days of December. In this case, the COP was always above 3, even though we had higher ventilation rates. We experimented with higher ventilation rates because of dust accumulation inside the building. The total energy consumption of the building was 2,400 kilowatt hours. Again, the PVs covered approximately 20% of it. And the compressor in this case contributed only to 13% of the total consumption, achieving a seasonal COP of 3.65 for the heating mode, very close compared to the seasonal COP for the whole year for the heating mode. Again, that was 3.77. What it is interesting is that the consumption of the exhaust fan was more than 50%. We experimented with a bigger fan in order to mitigate the dust buildup inside the building. And the fan was quite big and operating non-stop. This is something that mitigated somehow the problem, but still needs more work to optimize the performance. So, concluding, the heat pump maintained adequate indoor temperature even during heat waves, with satisfactory COP for both heating and cooling. The integrated PV system led us to avoid emissions of approximately 5 tons of CO2 equivalents for the whole year. Of course, there is room for improvement, especially for the integration of ventilation and how we control it. And one of the important outcomes is that special attention should be paid from the early design stage. That's all. Thank you for your attention.
Is there a question for Dimitris?
Just a curiosity, what do you think about an idea for a possible next project that is the implementation of a geothermal heat exchanger to support the heat pump, in particular for the summer period?
That should be interesting. Also considering the fact that other heat pumps, as the one you presented earlier, Stefano, performed really well as a ground source. I think that it would enhance the heat pump's performance, but I think that the most crucial part in Lane Hen's facility in the poultry houses is how you will combine the heat pump and the ventilation rates. That since poultry houses need very high ventilation rates that decrease, let's say, the efficiency of the heat pump. But it should be interesting.
If you compare the seasonal COP we achieved in the Agricultural University of Athens in the Lane Hen's room with the seasonal COP of the Italian case, what is the comparison? Just to have an idea how the geothermal heat source affects to the efficiency of such systems, I mean,
yes.
Of heat pump systems.
In the Italian case, we had only heating. Here in the poultry house, we have also cooling.
In heating mode, let's say.
They are close, could be better. I mean, the Italian case has better COPs, probably because of the ground source.
Yeah. For sure, because of the ground source. Okay.
Another question? Yeah, Lucas?
Let me place a question, if you have time, to this COP. The 3.77 is the weighted, so you divided the whole kilowatt hours of heat per year
yes,
with the electrical.
The heating kilowatt hours in a yearly basis divided with the energy consumption of the heat pump during the electricity for this period.
Because if it in summer is it quite higher, no? Because you don't use that much energy in summer compared to the winter, no? So it's weighted to the winter season, no?
Yes, and here I just saw a mistake. Here we have cooling, heating mode, not cooling mode. Maybe that caused the misunderstanding.
Oh, perfect. Okay. Thank you.
Okay. Then maybe a very brief question if someone has one. Yeah, it was not brief.
So, in your last slide, what do you mean by the last point?
It is crucial to have engineers and livestock managers get in contact and communicate in a more efficient way, and the one understand the other so that the engineers can design in a more precise way, more fitting to the needs of the livestock sector, because it is many times they are unique.
Perfect. Thank you.
Okay, thank you very much. So our next talk is by Hans Hoes from Terra Energy on geothermal applications for livestock.
Okay, good afternoon. I'm Hans Hoes from Terra Energy. We are experts not in livestock, but specifically in geothermal energy. So we try to combine those two. So I will also try to give an answer to the last questions. We're talking about shallow geothermal. So you also have deep geothermal, what you see on this graph. We're not going to talk about that, 1, 2, 3 kilometers of depth. We talk about investments of 5 to 10 million euro. We're not talking about that. We're talking about shallow geothermal, not shallow 1, 2 meters, but shallow as is very well demonstrated in Italy and explained by Stefano. It's a depth of, let's say, 10, 20, 30 meters up to 200 meters of depth. And you typically have two systems. Just a short explanation, time is limited. You can use groundwater as an energy transport medium. And then you have two wells, and you use the groundwater itself. It's the best way to do it, because the groundwater is in the underground. It's in touch with the sediments, so it's the best way to have a energy exchange in the underground. You pump water, you get the energy out of it, and you pump it back, so it's cooled down. And you do it the opposite way. And you see a photograph of an example of a wellhead. And typically you do it this way, or you in a heating mode, you extract heat while cooling down the groundwater. And in that case, you typically use a heat pump, or you do the opposite. And that's, of course, the very interesting thing when you do a heating phase an entire winter. Groundwater is cooled down, so you get a cold volume in the underground, and that can be used for direct cooling. That's a very important thing to mention. When you use it directly, you get passive cooling, very efficient cooling in this way. The other system, I want to be short here, that's already explained by Stefano. It's a borehole thermal energy system where you use vertical loops that you put in the underground and you exchange energy while circulating this fluid, typically a water glycol mixture. You can do it several ways. Typically, a single U or W pipe is used, or loop is used, or you can also use a coaxial pipe, typically in high-density polyethylene. So we did a case study for the same farm that already mentioned several times here today, a pig farm in Belgium. And what's the concept? The concept is, in this case, we would use also the same system, but in a different way. The B-test system with the vertical loops. Why the B-test system? I'll come back to that later. So you see here the way it's used. You have a heat source, you have the heat production, you have the heat storage, heat cold always, and you have the consumers. So in this case, the source is the beta system, the geothermal system, and you have the two heat pumps. It's explained before, where you have the low temperature heating, that's for the floor heating, and the high temperature heating for the twin tubes for heating, but also for tap water storage for showers and cleaning. And then specifically, and that's new of course, the beta system can be used via a heat exchanger directly for cooling. That's a passive cooling system. You can do that, limited with the twin tubes. It's not very efficient, but you can use it to cool it a little bit down. So the benefits are you have renewable heating with high efficiency, passive cooling with very high efficiency, and what is of course important is the avoidance of overheating in summer. and a better animal welfare. So you have also sort of higher production rate. The 220 megawatt hours of heating a year that is needed, we created a heating profile because that's necessary to examine the solution with the geothermal. And we added the possible cooling. And you see, we estimate that you can cool about 11 megawatt hours a year. And you see the 220 megawatt hours, so there is a strong imbalance. But that's more or less with the existing installation, the maximum thing you can do with passive cooling. Just to give you an idea, this will mean 18 W loops at a depth of 190 meters, given, of course, the total capacity of the heat pump in this case. Why it is 190 meters? That's a strange figure, but that's what legislation is in Belgium for a maximum depth at this point. Typically, it's 150 meters, but at this point, over this site, it's 190 meters. And in the red and blue graph, you see the in and outs of the borehole heat exchangers. And on the top right, you see the geothermal, the geological subscription of the underground. When you do an energetic and a financial evaluation, you have, of course, a much higher investment for the geothermal, about 118,000. But, of course, you have also a benefit when savings on energy and maintenance cost. And that's a dangerous one, an increased production efficiency. We did an analysis of the number of overheating hours and the impact it could have on animal welfare, but also on production. So that's certainly a number that should be verified. And then you get a simple payback time of about 13 years. If compared with a gas boiler, if compared with an air-water heat pump, what is eventually the solution that is done within the demonstration of the RES4LIVE project, with a focus on passive cooling, you get here the numbers and a simple payback time of about 10 years. You can also do a total actual cost or the total cost of ownership calculation. It's not so difficult to see what's meant in this graph. In the beginning, total left, you see the initial investment. Of course, the initial investment for the geothermal is the highest. The air-water heat pump is a little bit between, and the gas boiler is the lowest, is the blue one. But of course, the blue one will have a higher energy price every year, and the green one the lowest. And then you see, of course, the intersection that gives you some sort of dynamic payback time between 9.1 and 11.2 years, with a given interest, inflation, and energy factor rates, which are, of course, not always for everyone the same. And in total, after, in this case, 30 years, you have a total expense of the numbers you see here. I'm going to be fast for the second concept, just showing you that this concept is also possible focusing on passive and active cooling, because when you use the heat pump for tap water storage and for the showering, for instance, that's all year. When you use it in summer, you can store the cold and use it for cooling. At the same time, use it. And that's the idea. You can use it together. And then you have a combination of passive and active cooling. And of course, you need to add air coils to do the cooling of the air. In this case, you have two blue lines. That's the passive cool line and the active cool line in this specific situation. Even in this case, you can limit the number of loops from 18 to 16 because you have a better balance in the underground. So in this case, if we compare with an air-water heat pump, where we should also, or we can also use it for cooling, if we should do so. And then you see these figures and a simple payback time of 13 years and a dynamic payback time of about 11 or 12 years, let's say. Then finally, some remarks. What's the potential of geothermal energy? Just so in geothermal energy offer best opportunities when applying with heat extraction and heat injection. We saw a very, very nice example in Golinelli farm, where it's used in that way as heat storage from the sun and recuperating or regenerating this heat with a heat pump. But you can also do the cooling part with it, cooling it further down and using it for passive cooling and even for active cooling, using the geothermal system as a heat dump. I want to say something of the difference between A-test and B-test, the aquifer system and the borehole system. The B-test system has less geological restrictions. You can almost use it everywhere. A-test is a little bit complex, more complex, requires a suitable aquifer. And typically, B-test is cheaper for small installations, and A-test becomes interesting when the thermal power exceeds, that's our experience, let's say 100 to 150 kilowatt, let's say 150 kilowatt. This is 3 times the size of the Belgian pig farm in this example. So it's certainly not possible to use it at small farms. Farm cooling, how do you integrate it? Several examples. The most simple example is, of course, the floor cooling, sorry. When you have floor heating, you can also use floor cooling. But you need to remember, that, of course, that you cool it not too far down because you get condensation, but it's perfectly possible to do the cooling. And you can do the air cooling with or without condensation, of course, and you have several ways of dealing with it, a classic air coil or heat exchangers that are placed in the air supply channel in any way. Then the applicability in Europe, it's very important to state this, that there are 2 main differences. The undisturbed ground temperature in Central Europe is about 11, 12 degrees. In Sweden, it's a little bit less. And of course, in southern Europe, Spain, Italy, Greece, it's higher. It's about 16, 17 degrees. So it's typically gives less chances for passive cooling, although it is possible. But typically you will see that there is a better thermal balancing. In Central Europe you have much more heating demand than cooling demand, so you have an unbalance. And when you go further south, this balance gets better, but it's getting harder to do the passive cooling, but you can do, as also demonstrated in Greece, with a passive cooling system. Which application, every livestock applications with need for heating and with issues for heat stress. And then finally some general conclusions. Geothermal heating creates efficient heating while cooling down the subsurface, and this cold can also be used for farm cooling, preferably passive, of course, because of the high efficiency. Just to give you an idea, the efficiency rate is with passive cooling is between 15 and 25. So that's of course very interesting to do, because otherwise the cooling of farms is not is rather expensive, of course. Then at current energy prices and that the prices that are used in this example, it's a payback time dynamic between 10 and 15. A very important benefits, dus the avoiding of heat stress. And finally, a final remark is that, of course, the ratio between the fossil fuel versus electricity price, of course, it's always better to do the electricity in a renewable way, but when you have to pay for it, the ratio is important. And in Belgium, it's very not good, let's say. We have a ratio that's about the highest for all over Europe. Okay. I thank you.
We have time for a short question. Manon?
Hello. So you talk about cooling through the underfloor heating. Thank you for your presentation, by the way. So you talk about cooling through the underfloor heating, but most of the time the underfloor heating is used for piglets. Then how will you avoid that you cool a compartment with underfloor heating and not cool the piglets?
Yeah, that's a good question. In this example, it's not foreseen to do the cooling with floor cooling.
I know, but now we have no cooling
because it's the piglets,
strategy.
you cool the piglets, and that's not the idea, of course. So in the example of for the ILVO farm, we should do the cooling with the twin tubes and with an extra cooling coil in the air ventilation system.
Yeah. Well, yeah. Now we actually have the same. Yeah.
Yeah, I don't know the word in English, but the time is up. Thank you very much, Hans, for your presentation. It was really interesting. Next up is, again, Dimitris Styris. He's going to talk about the life cycle impact assessments.
Hello again. So, the solutions proposed by the project that you had the chance to get to know more about earlier. What we wanted to achieve with designing, installing with these technologies was the replacement of fossil energy use utilizing renewable energy sources. But in order to be sure that this does not burden the environment, an environmental impact assessment of these systems was deemed necessary. And the reasons behind it is that we need to ensure that the transition to renewable energy is both effective and sustainable, to be able to evaluate potential trade-offs so that their implementation have a net positive impact. Of course, provide the stakeholders that devise strategies promoting sustainability. And last but not least, gain more insight into a less studied area of literature, meaning renewable energy systems are studied in terms of life cycle assessment. The same goes for livestock facilities, but the combination of two is not that studied yet. This work, we will present again the installation in Golinelli pig farm in Modena province in Italy. Of course, it consists of several different barns, but the interventions that our study focuses are the interventions in the nursery barn that produces approximately 13,500 winners annually. As you saw in the previous presentations, here we have a multi-source heat pump, photovoltaic thermal collectors, borehole thermal energy storage system, and of course smart control. We will focus on the three main interventions. The objective is to assess the environmental performance of these innovative energy systems that are deployed at this commercial facility by applying the environmental life cycle assessment methodology. It is, since the nature of the project is technology oriented, it is highly focused on these integrated systems components described earlier. To estimate the environmental performance, we used the indicators that are in accordance with the EU product environmental footprint method. Now going into more detail concerning the system boundaries and the functional unit that was chosen, we use the cradle to farm gate environmental LCA analysis, with a functional unit of 1 kilogram of wind piglet at the gate of the nursery barn. In the simplified flowchart below, you can see the system boundaries, the renewable energy systems, as well as the existing equipment, and of course the product flows. Winners go inside the nursery barn and the wind pigs are going out of it. You can see the electrical and thermal energy flows, as well as the fuel flows that are substituted. In this case, the system substitutes an LPG boiler consuming fuel. The inventory created for each system in order to assess its environmental impact was based on the raw material extraction and transformation, their assembly, and finally the transportation and installation to the farm. The models have been developed in the CIMA Pro software using the attributional modeling approach in order to estimate the environmental burden. And as I said before, this was done in terms of per kilogram of wind piglets in annual basis. What was deemed necessary was the elaboration of a detailed bill of materials and relevant data processing for inventorying the renewable energy technologies. Since we have innovative technologies, access to all the components, we believe that this can add to the innovation of the project results. How these bill of materials were translated into LCA models. Below you can see for the case of the heat pump in the Golinelli farm, we have different resources listed in terms of materials and fuels used, as well as the energy in terms of electricity and heat necessary for to build its component and its unit as a whole. Through the technology developers that are part of our consortium, as well as of other manufacturers of similar technologies or similar components, we gained access to the mass, to the weight of its material used in each component, and mostly through literature, we chose the most suitable processes in the databases that we have at our disposal to model each step. Now, going to the results. The impacts in terms of resource use and climate change per kilogram of wind piglet will be presented for each of these technologies. But before that, and only to use it as a measure of comparison, we present the environmental impact that the electricity use had for this facility before the installation of the equipment. As you can see, it contributed in terms of resource use, we have 6.46 megajoules of energy and approximately 0.4 kilograms of CO2 equivalents. Again, you have to bear in mind that this is expressed in annually per kilogram of wind piglet. For the borehole thermal energy storage system, we can see that we have a very low impact, both in terms of resource use and climate change. you can see that it is orders of magnitude lower than the impact that the electricity has, approximately 0.062% compared to the electricity in terms of resource use, and 0.074% in terms of climate change, of CO2 equivalents. This is more or less the case for the heat pump. Again, we have a very low impact compared to electricity use. Only the case of PVTs, we have a slightly bigger impact, but again, if we compare it with electricity use, it is much smaller. For example, it's 0.59% for the resource use and 0.72% for the climate change. Now, what we want to also to see is how this is contributed for its technology, what material contributes most to the impact, to the environmental impact, but this needs a bit further refinement, because we would like also to express it in terms of component and not only material. So concluding, what we can see is that this equipment contributes very low to the annual environmental footprint of the piglets at the nursery barn gate, compared with the footprint that the electricity input before the installation has. And these results will be used to investigate the environmental performance, if the environmental performance is improved after the installation of the integrated RES system. Thank you.
Questions for Dimitris?
I have one, so surprisingly. It's a curiosity, actually. You were comparing two different environmental management systems, so cooling and heating. Why did you choose as a functional unit a production of 1 kilogram instead of cost of heating 1 Celsius or cooling 1 Celsius?
Thank you. This is actually something that we discussed a lot in the first months of the project. It seems that in the literature, focusing on livestock production, the functional unit was expressed in terms of the product, what the farm produces. So it is in our intention to also express it in terms of energy, like heating or cooling kilowatt hours, but we chose to begin with expressing it in terms of product.
Thank you.
Any more questions? There's still time. Dimitris, do you plan to do the same analysis also for the other farms?
Yes, actually, by the end of this month, the report for the analyzing the performance of the systems for all farms of the project will be finalized. For the Italian, Greek, and Belgian case, the functional unit will be the product of the farm. In the German one, we will, because we have different systems, not installed in a specific livestock environment, will be expressed in terms of the energy that, for example, the bio-CNG offers.
And how generalizable are the results?
This is an issue with life cycle assessment in general, because everyone is expressing the results slightly different. I think that expressing the results in terms of using as another functional unit, the energy, will make them more comparable with the literature, focusing on the technologies, at least.
True. Okay. Okay, if there are no further questions, then thank you very much, Dimitris. So our next talk is by Li Rong. Unfortunately, she was not able to join us here. So she, sorry. She recorded her presentation, but I do think that she's online. So she will be available for questions afterwards, maybe through Ricardo. We will see how it works. But first, let's hear her talk. So the video can start now. Thank you very much.
Hi everyone, good afternoon. This is Li Rong from Aarhus University in Denmark. Today I'm going to talk about modeling thermal status of pigs and cattle via a literature review. First, I will give a brief introduction of the background, presenting the heat transfer processes within the body and the heat exchange processes between the animal bodies and its surroundings, which will lead to a couple of questions where we are and what could be improved in terms of modeling the thermal status of animals. Then I will present the methods that have been adopted in conducting the literature review. After that, I would like to share some of the findings and elaborate on those results a bit. Finally, I will present a short summary and share some of my own thought with you. Because of the metabolic heat production and the inquiry of maintaining the body temperature constant, the heat produced within the body must be released. So the heat can be released via convection because of the air movement around the animal's body if the air temperature is lower than the animal's body surface temperature. The heat can be released via thermal radiation between the animal's body surfaces and the surrounding surfaces. The heat can also be released via conduction, especially when animals are lying down. There is a big contact surface between the animal's body and the floor. And the heat can also be released via respiration. For cattle, part of the heat will be also released via the sweat evaporation if the cattle is sweating, because the cattle have sweat glands, but pigs don't have. Also, the cattle is normally raised in naturally ventilated barn with uninsulated roofs. So when we talk about heat exchange between the animals and their surrounding, solar radiation is another very important environmental factor to be considered. Okay, so let's say if the heat can be balanced within the animal's body, we say they are actually in the thermal neutral zone. It means that the heat can be released without extra effort. So what does it mean, extra effort? So, for example, when the animals are exposed to the heat stress, the body will do some physiological regulations. For example, they will increase the respiration rate. We call that is panting. They will regulate the skin blood flow rate so that more heat in the core body will be brought into the skin surface that can be released from there. We call this process is vasodilatation. And they can change their behavior. They can reduce the feed intake to reduce the metabolic heat production. So, we have talked about the heat exchange between the animals and the surroundings. And we also talked about the physiological responses when the animals are exposed to heat stress. there are studies actually focus on both sides individually, and there are very few actually can combine those two mechanisms in the modeling of thermal status of animals. So, after we know the mechanisms of heat transfer within the animal body and heat exchange processes between animals and their surroundings, it actually brought us some questions. How has the thermal status of pigs and cattle been modeled? Have we considered the heat accumulations? Have we considered actually the physiological regulations continuously in the mechanistic models of thermal status of animals? How have these models been applied in practical productions? And what could be improved in the future? So we looked into the literature, trying to find out if we are able to find the answer for those questions. So we used the database of Web of Science of Scopers up to March of 2024. And the language is limited to English. And we use the words swine, or pig, or sow, or cattle, or cow in the keywords searching, combined with the keywords modeling or modeling. And then we used the word thermal or heat searched in the abstract. And the literature review conducted following the protocol of ROSES. So because the literature review focuses on the heat transfer from the core body to the skin fur surfaces, and then it will be released from the surfaces to the surrounding environment. Therefore, the studies focus on the predicting the indoor thermal environment has been excluded. So we found 480 papers via the database of Web of Science and Scopers, and 2 from other sources. And there are 28 duplicates which removed. After title and abstract screen, we have 64 papers left for full papers reading. It turns out 23 for pigs and 39 for cattle. So here are some examples for predicting the or modeling the thermal status of pigs. We divided them into empirical model, mechanistic model, and machine learning in the next slides. So what does it mean, empirical model? It means, okay, I have a responsive variable. Normally, for example, is skin temperature or rectal temperature. And then I have some environmental factors monitored in the bar. And then I try to use the regression equations to correlate the response variable and the model input. So basically, this empirical model, their forms relatively easy, but they're developed based on given conditions, so it's difficult to generalize them. Mechanistic model means that they are actually using the input, for example, the peak weight, the environmental factors like ambient air temperature, wind speed, and the relative humidity as the input, and then they describe the heat exchange processes, borrowing the heat transfer principles like convection, conduction, and radiation to predict the response variable like skin temperature and body temperature. So the machine learning models, they are basically correlate the responsive data, and then based on the model input to predict the body temperature or the skin surface temperature, for example. So the empirical model was obtained from field tests or from the lab without considering the physical mechanisms of heat transfer, but analyzed data by employing multiple variable regressions. So the model is simple to use, but it's also difficult to generalize. It seems that there are more studies have employed machine learning recently. However, how to verify and apply them in practice maybe need more attention. The mechanistic models focused very much on heat exchange between animals and environment. We call this is passive system, but not much on how to connect the passive system with the active system, which describes the physiological regulations. We have looked into the literature and found that there are very few studies actually working where we can find physiological regulations for pigs. So it means the experimental data collected from tests on the physiological regulations of pigs are very valuable for developing a mechanistic model that can combine or integrate the physiological responses into the mechanistic modeling of the heat exchanges or heat transfer, so that we can apply them into controller and or digital twins. For cattle, there are also many empirical models which has not been presented in these slides. The most well-known is THI index, that is used to assess or predict if the cattle is under stress or not. And there are different revised versions of THI by considering maybe airspeed influence, radiations influence, and then convert them or predict effective temperature that the cattle can perceive. And there are also more studies actually found in the literature about the mechanistic model. And the machine learning actually has been used for many years in the studies focusing on cattle to predict like rectal temperature, respiratory rate. One good example is one study from 1994 and 2005. So for the cattle, many studies developed thermal indices to assess the heat stress of cattle, although they are not shown on the slides. Machine learning was adopted more than 2 decades ago for predicting the heat stress of cattle. More studies actually can be found recently. However, one of the challenges could be if the large amount of data is available for training and optimization of those models. Generally, the mechanistic model studied the heat exchange between animals and their surroundings, and the thermoregulation mechanisms individually. Studies combining those mechanisms are quite few. It is noticed that physiological, behavioral, and production indicators interact with each other, but they have been examined separately to facilitate the analysis. So, what we could do is, how could we actually, to integrate the physiological responses of animals to describe these mechanisms by mathematical expressions that can be integrated into the mechanistic models of the heat transfer and heat exchange between the animals and surroundings. and it has been recognized that heat accumulation is very critical when assessing the heat stress for animals. So maybe it is required more work of modeling that can consider the dynamic heat transfer processes so that it can better serve in identification of heat stress of animals when it starts, while at the same time, we can minimize the energy and water consumption that is needed for the cooling system. So because of the limitation of the time, I will finish my presentation now. If you have any questions, I'm ready and happy to answer because I will be online. Thank you.
Yeah, I'm afraid we don't have time for the questions anymore because it's already time for the next time slot. So if you do have questions, send an email, Lirong, Aarhus University. I'm sure she will be happy to respond. And maybe in the chat someone can also ask questions and then she can respond directly in the chat. So our next speaker is Petros Demisitegenau, my colleague from ILVO, and he's going to talk about the effect of the renewable energy installations that we did on the comfort in a pig farm.
Yep. Thank you, Arisa, for your introduction. Also the organizers of the conference, and RES4LIVE for the opportunity to present the work here. So I'm going to talk the effect of this renewable energy transition that my colleagues were talking, and we successfully implemented in this pig farm that you can see here. This is our experiment pig farm, where we have, it's located in Melle, Belgium, and on average we house about 1,500 pigs in this facility. What had happened the last years in the time of RES4LIVE is we had a gas boiler which is consuming about 220 megawatt hour heat demand in the farm, and with RES4LIVE, of course, we have managed to replace this gas boiler into a renewable source or a heat pump. We basically installed two heat pumps like in a modular format, the lower one about 25 kilowatt and the higher one about 40 kilowatt. So the heat demand or the heating situation in our facility is in the past the gas boiler heated the circulating water to 70 degrees centigrade, and for the requirements in the floor heating, and so we have to cool it down to 40 degrees centigrade by mixing with cold water. What we did in RES4LIVE is with this modular heat pump, we could heat separately for the demand of air heaters and the domestic heat water. We just heat it to 62 degrees centigrade and it's directly supplied. And for the floor heating, we heat it to 42 degrees centigrade. And what I'm going to talk today is this is successfully done, but what is the effect in the animals compartment level? What has changed in the animals world? Because they don't speak, we placed some sensors around them to get to know how the environment evolved with this change in energy source. So in the left, what you see is a floor plan of our farm, which is around 35 meters by 75 meters. And we have got about 16 fattening compartments and 3 farrowing compartments. And we have got 3 wind piglet compartments. And in each of them, of course, I'm going to show in each of these compartments, then we placed temperature sensor, which is around 22 temperature sensors. These are all PT1000. And also we placed 1 temperature sensor outside to see what is the situation in the outside of this compartment and also outside the farm. And we have we placed around 8 and 1, in total 9 relative humidity sensor in the fattening compartment so that we can get a better calculation of this THI index and so to tell more into the comfort of the animals. So this is more or less how the sensors are placed, and if we see the data part, like which part we have seen. So when we were operating in the past with the gas boiler, we took a data, 3 months data from May to August in 2023. And after the installation, after the heat pump, of course, we took the same period, 3 months of data from May to August in 2024. And we were measuring temperature, relative humidity, and of course other parameters every 10 minutes, and that's used for my analysis and determining these THI indexes in the animal compartment level. And how the THI index is calculated is using this formula from the result of a research result from our colleagues at ELBO. Directly I will go to the results. What happened in the fattening compartments? I'm going to present the time evolution of average temperature when we were operating in the gas boiler. So more or less, when we were operating in gas boiler, the compartment temperature, the fattening compartment temperature fluctuates when it is empty. For instance, if you see compartment 1, so the red numbers that you see are like compartment numbers, and if you see compartment 1 earlier, it was empty, so that's why you see a lower temperature. When you see compartment 7 and 8, for instance, those are the times where it is fully occupied by the pigs, and it's just a naturally higher temperature. And you can see that the temperature fluctuates between 40 degrees centigrade and 28 degrees centigrade inside the compartment. This is just numbers, daily average. I would like to zoom in for some discussion to the situation in compartment 1. So in compartment 1, earlier days, it was just empty. And when the pigs come in, of course, what we do is we preheat the compartment, and then it's heated to 24 degrees centigrade, and when the pigs grow, of course, we start cooling down. So in the gas boiler time, this was done very fine, and it was successful. And when we changed to a heat pump, then we took all the data of that period that I said, the 3 months, from May to August 2024. You can see, of course, for instance, compartment 13, 14, 15, 16, at early days, they were empty. That's why the temperature very low, and just, again, the compartment temperature fluctuates between 24 and 18. And for some interest, if we go to compartment 1, you can see that at the start, when the pigs are introduced into the compartment, it's around 14 degrees centigrade, and it slowly drops to 21 degrees centigrade. This is a set point. It was made with the heat pump. At temperature level, we could achieve what we want. If we see what's happening in the farrowing compartments, the same is true. We could successfully substitute the gas boiler into a heat pump, and there is no significant change in the temperature, so we could maintain somewhat around 25 degrees centigrade in that place. And the drops that you can see in the graphs here are the times where the compartment is empty for cleaning purpose. So we have 2 compartments, and we work in a circle of 3 weeks, and just this is, so they are emptied and cleaned, and then the sauce come in for farrowing. Again, in the wind piglet compartments, the average daily temperature, more or less, is kept between 28 and 24 degrees centigrade as required, and this is also no change, but maybe more interesting is to talk in the animal comfort levels with THIs. In the gas boiler time, this is the situation, and I would like to draw your attention more into compartment 8, for instance. Let's zoom in and see. So in compartment 8, it's just more or less full in the measurement times, and THI levels fluctuate between 70 and a little bit less than 75 in these periods. And in the left, I have plotted also the outside temperature. You can see that pretty much the higher THI levels comes when the ambient temperature is hotter. And this is, and also there is some constant time shift between these two. So when the outside temperature is colder today, then you can see the effect into the rooms a little later or like the day after. And this gave us a very good indication that we have to do more and control more the environment to come up with a constant THI levels. And when in the heat pump times, more or less, it also fluctuates between 70 to 75 when the peaks are there inside the room. And I want to talk in the compartment 2. This is where it's full, and you can see that THI levels again fluctuated between 70 to a little bit higher than 75. Again, this is highly influenced by the outside temperature. These are the lessons that we learned, and to summarize, so we have got compartment 2, which was full in the measurement times, and in the heat pump, so the average THI level is around 72, and the outside temperature averaged, the outside daily temperature was averaged to be 19 degrees. And in the gas boiler time, it was also THI, so we could maintain a constant, similar animal comfort by changing the heat source or the technology, and this is, I would say, promising, but at the same time, creating new questions, what we can do to come up with a constant THI levels by controlling these technologies, and maybe to adapt something to go in line with outside temperature. In conclusion, the thermal evolution and environmental condition inside the animal compartment level is analyzed, and the RES systems, or the renewable energy systems, has supplied the required heating demand and more or less keeping the animal comfort similar to the gas boiler times. This was successful, and the need for modern or dynamic controllers is emphasized for optimal operation of these systems and just keeping the animal comfort as needed. Thank you very much for your attention. I'm here for questions.
There's time for questions.
I have one then. You
Okay.
know, if nobody
Please.
asks, I will ask you. I wanted to ask you the entire presentation, what is the outside temperature, and you showed it in the last.
Yeah.
Because you're talking about systems that try to separate the two. But have you had experience with other type of insulation systems, either for the building or for the individual cage, that do not require energy?
Yeah, we haven't looked into that for sure, but yeah, why I brought like this outside temperature or comparing the situation into this microclimate and what's happening in the outside is to get or to give an insight where we will be heading next, is to come up with either through insulation or implementation of a specialized controller to have constant THI levels or comfort levels in the animal. Yesterday I had a discussion with some colleagues, and there are some implementation with heat exchanger at preheaters to come up with a constant THI levels. That can be a starting point, but still I am not satisfied, and I would like to push it with the EAAP to more advanced controller to have a constant THI levels.
Just for curiosity, in your farm in Belgium, how's this? How the lowest temperature in the summer has been going in recent years? So is it stable? Because in Italy we had a heat wave after heat wave, and I thought, what is your lowest temperature in the summer, and how probable it is, or in the future?
Yeah, like I don't, when it comes to summer, I don't see the low temperatures, only the high temperatures, and it was around 35 or so we could see. That, and this was in early August, and we had already 28 and 30 degrees centigrade. Yeah.
Okay, if there are no further questions, then thank you, Petros.
Thank you very much.
And then to end the session, we have a talk from Lucas Wanasek. On the biogas to bio-CNG upgrades.
Thank you. Hello also from my side. To my field of expert, I have to tell you, I know something about livestock and animals, but my field of expert is related to mechanical engineering, especially to biogas and biofuel production. And this is also the part I did within this RES4LIVE project to come down with fossil emissions as a fossil consumptions in livestock farms. To the RES4LIVE project general overview, I will skip this because you have heard it today, and come up with especially with the task of the biogas biofuel production. So in this task, we covered the idea, or we focused on the idea to make green and fossil-free fuel, especially on and for livestock farms. It worked out especially for farms that have also the ability to produce biogas, or they have a small already existing biogas plant, which turns manure from livestock into biogas. In this task, we focused to make technology that already exists on the market in the large scale, so at approximately 100 cubic meters of biogas per hour, to bring it down to a small scale, to be able to have a farm filling station of green fuel for livestock farms. So that's the task. What was the idea to come down or to realize this small scale farm filling station, especially for livestock farms? It was, let me go to the next slide. It was the idea to make it really simple, to scale it down to a size of 10 cubic meters of biogas per hour, because the bigger plants, the 10 times bigger plants, they are too big for only farm filling of green fuel for the own purpose of the farm. How we reached that? We got deeply into the mechanical engineering of turning biogas as a manure to biogas, and biogas to bio-CNG fuel, that is a fossil-free fuel for tractors or harvesters or other vehicles. And we therefore we designed a hybrid compression, because the goal was to come down with OPEX and CAPEX costs for this technical solution. And we designed a closed cycle process with a hybrid compression to realize a 10 cubic meters per hour bio-CNG plant. To give you an overview about the technical data of this micro-bio-CNG plant, we named it. We started with the biogas from the sorry, I have to tell you, it was realized at the LVIT farm, pilot farm within the RES4LIVE project in Germany, and therefore we realized the pilot plant. So we started with the 10 cubic meters per hour biogas plant, and out of this 10 cubic meters, we are able to produce 4 to 5 norm cubic meters of CH4 per hour, and this can be highly compressed to bio-CNG that is a fuel for tractors or for CNG vehicles. due to we are here at an animal livestock related conference, I will skip some technical details and want to show you the novelties and the outcomes. So the result of the task was that we were able to with this hybrid compression and with this closed cycle one stage permeation of biogas to bio-CNG, we were able to so the first time on the market we were able to produce a plant, so a pilot plant. We built a pilot plant that could be produce the green fuel at a competitive level from the OPEX and CAPEX costs to fossil fuels. So that was the goal, and we achieved it with this downscaling options for this microbiology plant. Yeah. Here we have the hybrid compressor. So this was the key part, also the key finding we used to come down with the OPEX and CAPEX costs for such plants to make it feasible for livestock farms to produce their own fuel. You see here the hybrid compressor and in the green cycle. Only to let you know some mechanical engineering backgrounds to that. We designed a closed circle membrane permeation, and the key finding was that in comparison to the former plants, we did the process with only one compressor instead of two compressors, and so we came down with the costs of the total plant by 50%. And yeah, now to the findings, so to the results of this task. So it was, like mentioned, a mechanical engineering task. So I skipped some details to mechanical engineering. But what is really interesting, like Manon told us before, about 7% of the only about 7% of the emissions are caused by the energy consumption direct on livestock farms, and with the green fuel production out of slurry or out of manure, we also have the possibility to reduce the energy consumption not only at the farm but also at the feed production on the field for the animals. So in general, out of the slurry, we can make the green fuel not only for the purpose to drive vehicles on the farm, but also on the field. Key performance indicators from the pilot plant we investigated were the specific energy consumption of 0.94 kilowatt hours per cubic meters of biogas we need to transfer it from the raw biogas of slurry to a high compressed bio-CNG fuel for farm vehicles, tractors, and so on. What's another for you another interesting part maybe the quality of the biomethane. So tractors or other CNG vehicles need biofuel at a quality level of approximately 95% or higher, and with this 10 times smaller plant for farm filling of bio-CNG compared to the former market available plants, we achieved 96 to 97% of quality of the purified biomethane respective bio-CNG. So with this plant, we were first able to offer farmers a solution to produce their own green fuel out of manure, and related to the energy directive, renewable energy directive, the usage of slurry and manure in biogas plants reduces the greenhouse gas emissions at a very high level. So because instead of store the manure at a non-gas tight storage tank, you put it constantly in the biogas plant and turn it to energy. So that's the idea for turning the slurry to biogas in general. To come up with the cost calculations, like mentioned in former times, plant existed in a range of as a plant existed on the market with 100 cubic meters of biogas per hour, and now we achieved the goal to make a 10 cubic meters per hour biogas plant at the LVT farm, and there we had calculated costs as a total costs, OPEX and CAPEX, of 2.25 euro per kilogram CNG, which is more or less competitive, because you also earn the greenhouse gas certificates for this production of fuel. And for the bigger plant, the 35 cubic meters per hour plant, we gained full costs of 1.5 euro per kilogram, so also competitive. And to show you the data in some extracted figures that shows the potential of the bio-CNG. So one cow produces per year 289 cubic meters of biomethane, and with that biomethane you can drive 4,000 kilometers with the car. And 1 ton of wheat straw, for example, produces the bio-CNG for 3,600 kilometers. And another example, KTPL related data. 1 hectare of plowing with a rotary plow needs approximately 25 kilogram of bio-CNG. And to come up with a interesting fact, so 1 cow with the slurry of 1 cow, you can plow 8 hectare of arable land. So, and there are the conclusions, the summary, and I think together with the summary, I may ask you some questions about a little abstract topic for that conference. So maybe you have some questions to the engineering or to the usage of such plants.
Thank you. Question for Lucas.
I have one in the last second.
Yeah.
And Petros has one.
Ah, sorry.
Yes.
Okay. And then you go.
So Lucas, thank you very much for the nice presentation. My question is, maybe I have never asked it before. This bio-CNG, can we use it somewhere in the world, like Africa or application in other parts of the world? What do you think about that?
The question was if it's possible or it's feasible to use it also in other continents.
Yes, indeed.
Yeah. This plant could be used anywhere on the world, I think. So you need electricity or a generator for running the plant, and there are also there are existing projects in Brazil. So in South America that cover the same idea.
Okay, Michael, you had a quick question?
Yeah, very quick one. Really great solution, empowering, and I like the business metrics at the end, but I will ask you what they asked me in the pitching sessions. What's going to be the business model? So is it operated, sold to the farmer, system as a service, operated by a third party? Who's going to operate it?
We had it was not a project partner in the RES4LIVE from the first time on, because the initial project partner jumped out of the project. So we worked together with the Austrian company BioG, and they they developed and built with us the pilot plant, and they will be able to now transfer it to the market to farmers or livestock farms. They are interested in this technology. They can now already buy this.
Okay,
Yeah.
buy.
Yeah.
Okay, thank you very much, Lucas. And thanks to everyone for your presentations, for your attention. Special thanks to Michael for thinking about all the questions. So thanks a lot, and I hope you have a nice evening.